In this video, we're going to start to talk about section 6.4 and the idea of the convergence of a Taylor series. So in previous sections, we've talked about Taylor polynomials and Maclaurin polynomials, and Taylor series and Maclaurin series. The idea behind these was that they were supposed to be polynomials or polynomial-like things that were meant to try to approximate particular curves. And what we've done in the past couple sections is we saw kind of more generally that these were special kinds of power series, infinitely long polynomial things. And we saw that these infinitely long polynomial things could model different functions. And we could think about them as having domains, which we thought about as an interval of convergence. And we were curious in the last section, when we were given a particular function, how could we find a power series that models it? Well, one of the other things that we're going to be interested in here is that we might ask the question, is it ever going to be possible that when I have a Taylor series of a function, I find a very special Taylor series that models a function, will it ever be the case that that Taylor series, when written out forever, will actually converge to the entire function? Now, I'm going to go ahead and down below, I'm going to draw a picture to try to help illustrate this idea and some of the ideas that we're going to talk about in this section. To help save on some space and some time, I'm actually going to remove the proof from what we're about to do today, and I'm going to use this space down here to try to draw a quick picture. So keep in mind that what we've been attempting to do thus far is to say that if I had a function that I could sketch out here, I might need to make this a little bit smaller. But if I had some sort of a function that was maybe difficult to try and work with, maybe this is a complicated function, f of x. It's difficult maybe to plug numbers into this function. What we said is that we could create a polynomial. We could start at a value of x0, and we could start to go ahead and try to approximate what this polynomial or what this function would look like by starting with an initial point of connection and building maybe some sort of modeling polynomial. So this polynomial might model the curve somewhat well, like you can see here, maybe on like this interval around x0, my blue curve does a good job of modeling the black, and then it starts to break away. Well, what we're interested in is that if I was to keep taking this polynomial, which we've typically written as p sub n, where n stands for the degree of the polynomial, then if I was to let n continue to get larger, would this blue thing eventually line up with the black thing perfectly? Not roughly, but perfectly. Well, in order to try to understand that, we have to go ahead and take a look at this first definition. Let's suppose that the function f that we're working with is differentiable n times, like as many times realistically as we could want. Well then, if I form an nth degree Taylor polynomial of f, that's kind of like my blue thing. It's going to model the curve. And we already have a formula for that. Remember that if it was centered at x0, I'm going to have this x minus x0 to the k, and then I have this coefficient formula sitting in the front. But it's brand new here, and what we're about to define is this idea of a remainder. So we're curious about what would happen if I went to a specific x value after I've drawn a specific polynomial of degree n, and I took the function and subtracted the polynomial. Well, you can notice that like over here, if I was to do this, I can see that there exists a gap between the function and the polynomial. And so if I subtracted those y coordinates, I'm going to get some value. Maybe it's a value of 1 or a value of 6.7, who knows, but there's some sized gap there. And if I was to grab an x value over here and try to go ahead and measure the gap, if I do function minus the polynomial, I'm going to get some sort of a negative number. But either way, we call that value a remainder, specifically the nth remainder, because we'll notice that that size of the gap will change whenever I change my x coordinate, but it also changes if I was to change the blue polynomial. If I was to make it maybe a degree 7 polynomial over a degree 3 polynomial, the blue curve might look very different, and so these gaps might change. So we'll see here that every remainder is dependent on the value of n. it's also dependent on a value of x. Okay. Once we have that defined, we can go and start to take a look at our next important theorem in this particular section. So here's what we're going to say. Let's suppose f is infinitely differentiable. Okay, so we can take its derivative as many times as we want and plug in x0 and never get a problem. Okay, so this is a property that we're going to suppose is true about our function at x0, so at that initial point of contact. Well, then we can also say that if f of x is defined as p sub n of x, my blue polynomial, kind of just plus all of my remainders. Notice that this is just a rework of the statement that we had up here if I added p sub n of x to the other side. Okay. So if this is the case, and if it's the case that when I do the limit as n approaches infinity of my remainders, so if I let the blue polynomial continue to change and go higher and higher and higher degree, and if I do the limit then of all the remainders, and I get that that limit turns into 0 for all x values in, notice here I'm communicating an interval, so this is inside the interval of convergence. Keep in mind that this is equivalent to saying all values that are in the interval x0 minus r to x0 plus r. So if it's the case that the limit of the remainders turns into 0, those red gaps shrink away on some interval, then f is equal to its Taylor series on that interval. Now, this can sound at first like a fairly complicated statement, but it's actually a really simple statement. If I'm going back to the main question of the section, how could I show that the entire function, or the entire blue polynomial, will converge to the function? Well, the only way that the blue thing and the black thing will be the same is if all of the red gaps disappear. If all the gaps are no longer in existence, then I know for sure that these two things are identical. And that's actually what we've written here, is that as long as the remainders move towards 0 on some interval of values, maybe not everywhere, then we can say that f, the black function, is equal to its blue Taylor series on that interval. If there's no more gaps, the two things have to match. So that almost seems fairly intuitive. If you're interested in the proof of that particular statement, of course you can look in the notes that are up online. So I'm going to go ahead here and take a look at one final statement in this video, and it is the theorem that kind of sets the stage for what exactly is this section all about. So here's what we've seen so far. From the above theorem, we can probably see that the key to showing that a function is entirely equal to its Taylor series is showing that, well then, all the remainders have to go to 0 for every value of x that we're interested in. That, if I want to show that it works for all x's, well then I actually have to show the remainder disappears at every single possible x value. So we need a theorem that can provide us some information about the sizes of those red gaps. And this is the theorem that we call Taylor's theorem. It's sometimes also referred to as Taylor's inequality, and it's got somewhat of a complicated sounding statement, but what we'll see is that it's actually very similar to some statements that we've seen in the past. So here's what it says. Suppose f of x is differentiable n plus 1 times at x0. Okay, so again, there's an initial point of contact x0. Let's assume that we can take derivatives of our function f, keep plugging in x0, and we can do that n plus 1 times. Okay. If we can do that, and if we can do something else, we can make a really powerful conclusion. Here's the second thing we need to guarantee before we get a nice conclusion. If it's then the case that when I do the n plus first derivative of the function f, and I absolute value it, and if I can claim that that graph is going to be less than or equal to a y value of m on an interval containing x naught, say an interval from a to b, where x naught is one of the values inside of that interval, then the remainder r sub n of x satisfies the following inequality. Now, before I write that inequality, I just want to go back to the statement, because this is often the statement where people get a bit confused. Notice that this is actually very similar to some properties that we established back when we dealt with Simpson's rule and midpoint rule and trapezoid rules, where we had to find something. I think we had it as a value of k. Here it's just labeled as a value of m. But it said that we had to go ahead and find a particular derivative of our function, absolute value that, look at that graph on an interval, and then find a y value that was always bigger. And if I can do that, then I can write down the following. Here's a property that must be true about my remainder. If I absolute value the remainder, so again, I don't care if I get a positive gap or a negative sized gap, but whatever gap I get after absolute valuing must be smaller than or equal to the following fraction. So I'm going to have m, that number that's here, going to be put on top. I'm going to have an n plus 1 factorial, and then I'm going to be multiplied by x minus x naught to the power of n plus 1. And that this would have to be true for all x values in the interval a to b. Okay, this is a very complicated sounding theorem, but in actuality it's surprisingly simple. If you break down to the bare bones, what it's actually saying is it's giving us an ability to approximate how big our remainders might be on an interval. Not on the whole function, but on an interval. And so what it says is if you can meet the conditions, and then you have an interval from a to b, maybe that's an interval like up here in my picture. Maybe I could create an interval up here that says from a over to b. And so maybe on this interval, I have the ability to estimate what the sizes of the gaps are going to be. And notice that can be done without ever creating the actual Taylor polynomial. All you need to know is this value of n, the degree of the polynomial, the value x, where you want to measure the size of the gap. You need to have this m value, which we have to determine ahead of time, and everything else should be given, because we should already know our x naught value where we're centered. So in the next video, we'll take a look at some examples of how we can actually try to utilize this theorem to show some pretty surprising and powerful results.